Hello and welcome to this section of the course, Environmental Controls for Technology. My name's Gerd Berner and I'll be presenting. So this section will discuss the physical ways we need to protect our technology systems at sea. As we know, technology is sensitive to many external factors such as temperature and humidity, and all technology equipment has a set of parameters that it can operate within, and should it fall outside those parameters, technology can become unreliable or fail outright. So we'll discuss here some considerations to be aware of as seafarers, because as seafarers we're on the front line of users of the system and can often find ourselves in situations where there are limited support resources available. Where support is available, it may be remote. And the ability to communicate with shore-based engineers that may come on board to install, to upgrade, repair, or perform surveys on technology can be a big advantage to yourself as a user of the system and someone who may then have to take that system to sea, and also to your organisation. So, power quality. Now, all technology systems require electrical power, and power quality is something that's often not thought about very much. It's particularly relevant on board ship because we have relatively small generating plants, and we have lots of relatively large electrical loads that are started and stopped. Large loads like bow thrusters, hotel load, refrigerated containers. All of these electrical loads, as they start and stop, cause interference in the electrical system. Each time a circuit breaker or a motor starter engages and disengages, it causes transients on the electrical system. Now, many vessels are designed using what's known as soft starters to help reduce transients. So an analogy, if you like, it's possible to start electric motors by directly connecting them to the electrical system. This is known as DOL, direct online starting. Imagine, if you will, that you are driving a car and you, from a standing position, you accelerate by putting your foot flat to the floor. As you can imagine, that creates quite a strain on the machinery. A soft starter, if you like, is the equivalent of gently accelerating the car up to speed, and this has the effect of producing less interference on the electrical system, and we'll see shortly why interference on the electrical system can impact our technology systems. There is a need. Most technology systems have are quite fussy about a steady voltage and frequency being supplied to it to match its specification. And as the electrical system deviates outside of those set parameters, there can be negative effects on that technology. So why is this a concern? Electrical noise can find its way into electronic equipment that operates using very small signal voltages. So noise that can be induced into a piece of equipment can create transpose a fake signal on top of a legitimate signal, causing a piece of equipment to malfunction. These induced voltages can also exceed the insulation rating of components within technology, resulting in an outright failure of that technology. So there will always be a certain amount of noise, and a ship at sea can be considered quite having a high level of electrical noise, and as such, equipment that you find there is often engineered very carefully to protect it from elements of electrical noise. So there are a number of ways of doing this, and some will be familiar to us. We've all seen line filters available in computer stores that can protect our equipment from noise coming in on supply lines. These are domestic versions in an industrial situation like on board a ship. Typically they're a little bit more robust. In addition to this, we have concepts of shielding, and what that essentially means is the boxes that equipment come in are built to absorb radiated electrical fields that can result in noise being inducted into the equipment. Also, cables are shielded to protect as they traverse possibly near high power electrical cables. The shielded nature of cables prevents the induction of electrical noise, or reduces it to an acceptable level. So why do we need to know this? You may well say, this is a question for engineers and technicians. It's always good background knowledge to understand, and also if you're part of a piece of work where perhaps you've got engineers coming on board to install a new piece of equipment, it's always good to be able to ask and critically appraise perhaps the siting of the equipment. If something's being installed next to a very high energy piece of electrical equipment like a generator, always good to consider and potentially ask a question that could prevent a problem further down the line. Okay, power quality. Reliability and redundancy. So we have a situation where continuous power on board ship is a critical safety requirement in many cases. And navigational equipment, equipment that obviously provides manoeuvring capability, has to be maintained at a very high level of availability. So to achieve that, we have often emergency power supplies, battery, UPS, and UPS stands for uninterruptible power supply. You often find these within an equipment rack, and they have an internal battery and charger system that will provide ongoing power in the event of a failure of the mains. So in some cases, these systems are designed to provide power during the gap between the time it takes for a power failure to be sensed and the startup and connect sequence of the emergency generator. Emergency generator will typically run up within 45 seconds, which is the requirement, and emergency generation on board will have none of the same dependencies, so the emergency generator will have independent starting, compressed air. It'll have independent cooling and lubrication so that it can run in the event of failure of one of those systems in the auxiliaries. So you've had a failure caused the generators, the main generators to stop. The emergency generator won't be subject to the same dependencies, so it will be able to provide that emergency power. Now, in terms of technological equipment, equipment has a set life, and beyond that life, it is no longer considered serviceable and needs replacing. And care needs to be exercised that when equipment is replaced, it is replaced with equivalent equipment that meets the same standards, and also that the existing electrical installation is sufficient to provide the new system with its needs in terms of electrical supply. Now, once again, the engineers who are doing the changeover have hopefully considered these things. Supply circuits, cables and circuit breakers need to have sufficient capacity, and equipment shouldn't just be plugged in wherever it can be fitted. Now, the reason I raise this point is in discussions with seafarers, it's something that you do often hear about, where a new piece of equipment has been installed or a piece has been replaced, and due to an inconvenient sighting of the legacy piece of equipment, the equipment's been relocated, and you do hear about stories where someone has fitted a flexible cord and a plug and plugged that piece of critical navigation equipment into a power point that used to be used for the kettle. Now, the issue here is obviously around redundant power supplies. It's around, is that supply now insufficient to supply the new equipment, and is there the potential then that will then fail at a critical time, leaving the navigator without that piece of equipment. So as a deck watchkeeper who happens to be around when these types of operations are occurring, these replacements, these new installations, I would encourage you always to ask a question and challenge if something doesn't look quite right. If something's being installed and it doesn't look like it's being done in a convincing way, then ask the question, because ultimately the seafarers take this system to sea and have to rely on it. There is often pressure on shore-based engineers who may be doing an installation. There is obviously every vessel is looking for a fast turnaround. They will have a set period of time to deliver this piece of equipment and install it. And when things don't go as planned, there can be a lot of pressure to take shortcuts. So I would encourage you, once again, if something doesn't look right, the question should always be asked. Shock and vibration. Now, shock and vibration can also have a significant impact on technology. Vibration can cause the failure through fatigue of cables, circuit boards, components. It can loosen screws that result in circuit boards coming adrift and shorting out. These types of failures are rife in maritime applications because of the constant vibration of the engines caused by engines and propellers. One way this is counteracted is through vibration-proof mountings, so flexible mountings that allow for a certain amount of movement with the view to preventing the fatigue failure of cables and circuit board tracks. Sighting of equipment on the vessel. In some areas of the vessel are more prone to vibration. Obviously closer to the propeller and the steering flat is quite a high vibration area. Electronic equipment also has a maximum specified G-force that it can withstand. Historically, magnetic disk drives were quite susceptible to G-force. A maximum G-force of 4G is often specified. So this is typically more of an issue during shipping or freighting of equipment rather than once it's installed. However, obviously a vessel is quite a unique scenario for equipment. Manufacturers also have ways of detecting when operating parameters have been exceeded, and this is something that as perhaps a ship manager or someone who's accountable, perhaps as an engineer, if you're accountable for a piece of equipment, it's very important to note where there's a potential for running equipment outside of its operating parameters. There could be a possibility of an impact on warranty, and this can be quite an expensive issue to solve in the event that a key piece of equipment breaches its warranty conditions and is therefore no longer covered by warranty. Temperature and humidity. Cooling of equipment is also a critical function. When an equipment rack is installed, it will have been designed for a certain amount of thermal energy that'll have to be dissipated and a certain rate of airflow and clearances between the sides of the rack and the front and back and the equipment itself. And all of this design effort will be to ensure that the rate of airflow will carry away and dissipate the amount of thermal energy that is generated by the equipment. So if new equipment is being installed or additional equipment is being installed, there's a potential for a shortfall in the amount of heat rejection that can occur. So this is obviously another good question as a ship manager, as an officer on board, where engineers come on and want to make a change to the installed equipment. How much reserve cooling capacity is there in the system to support the addition of this new equipment? Now, if the vessel's operating at a certain latitude and new equipment comes in and is installed, there may be sufficient headroom in that heat rejection system to ensure that it works fine and continues to operate. However, the vessel heads to a new operating route closer to the equator, then you might find that all of a sudden the equipment becomes somewhat unreliable, or you start to have issues that you didn't have before. These are the types of considerations that should be made by the engineers making the change. Always good to have in the back of your mind that if the equipment starts to operate at temperatures outside of its defined operating parameters, then you may experience problems. So high ambient operating temperature impacts the ability for conductors and components to reject their heat into the surrounding air. And as a general rule of thumb, if you add up all the kilowatt ratings of the equipment and the power supplies, that's the effective heating power of all the equipment. There needs to be equivalent cooling power to keep that temperature at an acceptable level. If the air volume is small, if you've got a lot of equipment in a small room, small area, small compartment, it can heat up rapidly. And there will always be, I guess, a tendency to tuck the technology away out of sight and use a smaller space as is practical to do it. But we need to be aware of the implications of that. And that standard UFS 108 provides a little bit of background on the requirements around cooling technology. Humidity also presents a number of risks to technology. High humidity can result in corrosion, and as you're aware, we're already in a saltwater environment where corrosion is, there's already a higher risk of corrosion in a lot of equipment. High humidity also increases the opportunity for static discharge, and all of us are familiar with what static electricity is about. Even a very relatively innocuous action, friction, can lead to very high voltages, which can, if discharged through that piece of technology, can easily exceed the insulation rating, causing a permanent failure. So what I would suggest is, even at a very high level, if you're involved, you're a stakeholder in system replacement, adopt that system thinking mindset. So we've got energy in. Is the supply sufficient? These are some very basic questions, I guess, that can be considered. Is the supply sufficient? Is the device, is it currently covered by an emergency supply, a uninterruptible power supply? Is it one of these circuits on the emergency generator? And when we're talking about energy out, are the clearances sufficient for heat transfer? Does the heat rejection system have the sufficient capacity? So when we talk about chipboard technology, we are talking about very expensive assets. And as we've discussed over the last few slides, they can be sensitive to operating outside of specified operating parameters. Now, this can not only impact the safe operation and reliability of equipment, it can also have a financial impact on our organisation from the perspective of a warranty claim or a potential warranty claim in the event of failure. Manufacturers often install devices that are specifically in place to detect things like excessive temperature or supply voltage and frequency outside of the acceptable range. And these devices, while they might not be obvious to the users of the system, when the engineers pull this equipment apart to perform an inspection as part of a warranty claim, they will clearly see if there's been any material deviations from the spec, and that may have a financial impact in terms of a rejected claim. So important, because obviously we're all wanting to act in the interests of our own organisations, but bear in mind it's critical to make sure that we are, wherever possible, ensuring that technology is operating within those specifications. Acoustics. Now, generally when we speak about acoustics, we are speaking less about an impact on technology and more about an impact on the users who are in close proximity. So some technology systems are designed to be installed in areas where humans are performing their day-to-day tasks, and others are more suited to installation in a location such as a cabinet or a machine room where humans may have occasional access, and in some cases equipment, because we are talking about equipment that might have high capacity cooling fans, the level of noise that is generated by those devices, and some of these have a variable speed, so they can operate at high airflows and low airflows, and when they're operating in their high airflow modes, they can be really quite noisy. Server rooms can be quite noisy places to be. We do have to really think carefully about people's occupational health and safety. In most countries in the world, there are significant requirements, legislation around the noise levels that people can be exposed to as part of their jobs. And permanent hearing damage can result if we're overexposed to noise, particularly in an ongoing or continuous way. So this is relevant to us in our seafaring role. As I've said, oftentimes we have retrofitted equipment, we have replacement equipment. Another good question to be asking, particularly as many of you may find yourselves in the future in ship management roles, or perhaps are already in those roles, along with all the other questions around functional equivalency of equipment, or what specification, what are the capabilities of this equipment that we are installing. Another good one is around what level of noise will this equipment impose on the working environment. In earlier slides, we've discussed the importance of heat transfer and cooling effect to keep technology operating within its normal bounds of temperature and humidity. Now, contamination or contaminants can cause significant problems in a number of ways when it comes to operating technology. So firstly, as you can see on the right, we've got a filter that's blocked. Now, filters are the main way in which we remove contaminants and particles, dirt, dust from the air that's used to cool systems. So obviously a blocked filter in that way is essentially restricting the flow of air. Now, that reduction in airflow in itself can cause an issue because we have less cooling effect. It also causes downstream issues with the circulating fans that are providing that positive pressure to cool the downstream equipment. So we have fans labouring against essentially a blockage in an airflow column. We have, as you can see there, we have contaminants that are actually possibly making their way past the filter because it's exceeded its useful lifespan and function. The contaminants that pass the filter then can alight on the circuit boards or in various places within the technology enclosure, and they can be conductive. They can, through their contact, they can limit the amount of heat that is radiated from the surfaces. So there are a number of issues that result from contamination of this type. So it is critical that maintenance is kept up, and in my experience I have seen many times filters that get forgotten. They're tucked away in certain places, and in terms of the ongoing maintenance schedule, maybe there are some filters that are obvious or that are easy to get to, and those ones get maintained or replaced, and other ones that are tucked away or forgotten can fall out of the ongoing maintenance cycle. I will talk on the next slide on a real world maritime example of a technology contamination, and really a technology maintenance failure that led to a very close call with a vessel in New Zealand. So we'll cover that in the next slide. So this case study relates to this ferry that you can see to the right of screen called the Montistello. This vessel was on a liner run between two ports in New Zealand, and you can see the chart on the excerpt of the chart, Queen Charlotte Sound. Now this was a very lucky escape, because if you follow the waypoints on the chart, you can see the vessel was in very narrow waterways at the time of the incident, and anyone who's been to New Zealand will understand that it tends to be a very rocky shoreline, so the vessel could have run into serious issues had the incident occurred at a different place on the passage. You can see there are some quite sharp turns on the chart. Fortunately, the vessel was running straight when the failure occurred. The failure resulted from a contamination issue of a PLC, or a programmable logic controller, which is essentially an industrial computer. Now this PLC was responsible for power management on board. So essentially it was monitoring loads on the various switchboards, it was controlling supply, it was controlling synchronization of generation on the various generators. So it was playing a critical role in onboard power management. Now when the PLC failed, what happened was all of the generators were dropped off the switchboard, and essentially the ship was blacked out. Now, as a result, obviously the vessel lost propulsion and was essentially disabled. As a result, the the crew were forced to anchor, and essentially the vessel was in quite a vulnerable position until sometime later, when the power was able to be reconnected to the board through a recovery mechanism. The PLC itself was not able to be recovered to full operation, and the vessel had to return to port. Now, the upshot of the investigation was that, as we've heard, there was a contaminated supply of air from the engine room, and for a significant period there'd been no maintenance of the filters, and contaminated oil particles had found their way into the enclosure that controlled the PLC processor board, and the board itself had become contaminated. Now, in that situation, it's quite difficult to determine the exact cause of failure, but it's thought that the oil being deposited on the processor board had led to a breakdown of as I said earlier, the ability of that board to transfer its heat out to the cooling system. So, and also, I guess, considering there's a possibility there for the oil to, in some cases, oil is quite actually a good insulator, but in this case, it could have been a combination of the heat transfer failure and also potentially possible short circuits. The oil also being in place allows for a sticky medium for other possibly conductive dust to be deposited on the board itself, and so that was essentially the cause of the issue. Now, that was really just one of the issues that was identified as part of the problem. In terms of that technology, when the repair was attempted, it was discovered that no one on board the vessel, or in fact in the company, had knowledge of the software and the equipment to support that PLC. So, to restore the vessel to service, the PLC actually had to be replaced. They had to actually re-engineer the solution because no one had the ability to reload the software, and I don't believe there was actually an offline copy of the software that was running that critical system on board the vessel. So they essentially had to tear the whole system out and replace it to make the ship operational again. So that leads us to what does it take to support operational technology on board ships? And this is a critical question we should ask ourselves as users of technology, as engineers, as ship managers. These are the things that we need to have in place. So for any technology system, we have to have the software available, both the operating system, the application software. We need to have the skills on board in the event that software needs to be reinstalled or configured. We need to have availability of skills to deliver that, whether that's remotely via satellite communications or whether it's on board. And the more critical that function is, obviously the more robust we need, the more robust mechanism we need to ensure that technology is going to be available when it's needed. So any cables, any adapters that are needed to affect that transfer. In the event of that system from the case study I gave in New Zealand. An ideal situation may have been a replacement board. I mean, the ideal situation would have been that the technology wasn't contaminated via the oil from the engine room in the first place. However, if that had occurred, you need the ability for someone to swap that board out, put the new board in, and transfer the program in its current form, with any cables and adapters, a suitable laptop or whatever it is that's going to allow that service to be reinstated quickly. So that's the level of technology support that we really need. And we're talking around knowledge and training, that for that system to be, that critical system to be there without anyone on board or within the company having that level of knowledge to support that is an oversight, and that's evidenced by the experience that vessel lived through. Contingency planning is also a critical function. So where we have a fully automated system, for example, a power management system, there should be sufficient manual backup that would allow management of generators and loads, and it may be a more labour intensive, it may require people to be on watches rather than running as unmanned machinery space, but there should be sufficient knowledge and skill practiced such that manual methods can be adopted where we have a failure of automation. And we also need support from vendors. So if you have a particular vendor, and a system may actually be covered by multiple vendors, could be a hardware vendor, software vendor, we need the support from the relevant people to be able to keep our systems operational, to address our problems and questions, to keep the technology running as smoothly as possible. And physical security. Now, most of us are familiar with the concept of physical security. Now, when we have technology, ideally we want to limit access, physical access to those devices. We should only be letting people access those particular areas where there is a specific need for them to do so. Often we do see comms cabinets and machine rooms used for storage of all sorts of things, cleaning products. This not only does that have the potential to end up in a contamination situation, there can be other issues in terms of spillages and potential for combustible gases coming from products. So the strong advice there is to keep our machine rooms and comms cabinets locked, control access to those areas on an as-needed basis, and prevent the use of those areas for other purposes. Physical security is one of the easiest security disciplines, but it does often get overlooked. Generally, we find it degrades over time as people get complacent. Keys to these cabinets get shared, and over time, inevitably, someone wants to store something in there. And convenience typically overrides security a lot of times. So there are a number of, considering the cost and criticality of some of the equipment, that are stored in these areas, it's highly advisable to follow these guidelines. And in terms of a cybersecurity perspective, it is very much easier to, rather than hack a machine from external, trying to get remote access to it or access it via the network, oftentimes the simplest way to get access to that information is to simply steal the machine and take the drives out and image the drives and use forensic techniques to extract the data. So a few of my experiences in terms of physical security, a very large bank in Australia lost a whole pallet of new computers from their secure loading bay, complete with cameras and security guards. The thieves simply drove in and loaded the pallet up and left. And oftentimes someone who acts as though they belong there or looks like they belong there can get away with incredibly brazen acts. And that, typically a vessel import, there's a lot going on. It's a busy time and people getting access to certain technology, they may get away with things that, in the cold light of day, we might look back and go, wow, I can't believe that guy did that. But very brazen acts often occur when it comes to breaches of physical security. We've had other cases. There was a case of a government department in Australia where someone came to a data centre and stole a machine that was providing a service. The theft was only discovered when the users called the help desk to say, our system's not running, can someone check what's happened? And the person who was tasked with investigating went to the data centre to find the whole machine had been stolen. So as I said, very brazen, so always good to keep server rooms, comms cabinets locked and jealously guard the access to those areas. So that brings us to the end of this section. I have included the reference to the case study of the Monticello in New Zealand, which makes for a very interesting read if you're interested in environmental aspects of onboard technology. Thank you very much for your attention.